So when we're dealing with heterocycles or even just non-heterocyclic compounds that have a lone pair, a lot of times dealing with those lone pairs will give some trouble. So I want to talk about a few simple rules of thumb to keep in mind when dealing with lone pairs. Number one, only one lone pair on a given atom can contribute to the pi electron count. So don't try to double dip your electrons. So we saw that when we did pyrrole. So with pyrrole, the nitrogen had one lone pair, and we counted the lone pair as well as the double bonds for the pi electron count. But if we look at something like furan, where we have an oxygen instead, the oxygen has two lone pairs. But when doing your pi electrons and putting this in p orbitals, only one lone pair can go into a p orbital to contribute to the aromatic ring. Even in a case where you might want to count two. For example, in this ring right here. So if you count up the pi electrons and you just count 8, that's going to be anti-aromatic, or at least it's going to appear anti-aromatic. And you might be tempted to try to count the other lone pair to get you up to 10. You can't do that. In this case, what would happen is, so it looks like you're going to have 8 pi electrons, but because this is a larger ring, it will just not be planar. This will be non-aromatic. The second rule, if a given atom has a p orbital from a pi bond, and that pi bond is part of the pi electron count, then its lone pair cannot also be counted. Again, this is where you can't double dip. So we saw this previously with pyridine. So even though pyridine has a lone pair, you can't count it because the nitrogen already has a p orbital with the pi bond, and that's contributing to the aromatic ring. Here's another case, maybe with an oxygen. Like that, and this oxygen has a lone pair on it, but the double bond that's on the oxygen is already using up its p orbital. So there's the 6 pi electrons. The lone pair doesn't count. And the third rule is pretty simple. If counting a lone pair makes the molecule aromatic, then count it. If counting it makes the molecule anti-aromatic, then don't count it. Basically, leave that lone pair out of the p orbital, and the molecule will then not be conjugated, and it will be non-aromatic. So here's a case where we have an 8-membered ring. It's cyclic, and assuming we count the lone pairs, it'll be completely conjugated. So we would have a p orbital everywhere there's a double bond. And then if we count the nitrogen lone pair and the carbon lone pair, every carbon has a p orbital. So now if we do the pi electron count, here's 2, 4, 6, 7, 8, 9, and 10. So that is going to be a Huckel's number, or n equals 2. So in this case, we count those lone pairs because doing so makes the molecule aromatic. Now let's look at another example. Here's a 7-membered ring, and in this case, it's cyclic. If we count the lone pair, it will be completely conjugated. If we count it, we're going to have 2, 4, 6, 8 pi electrons. If you try to set 4n plus 2 equals 8, that's not going to work. So you do 4n equals 8, n equals 2. That's going to meet the criteria for anti-aromaticity. Well, the molecule doesn't want to be anti-aromatic. So instead, that lone pair won't go into a p orbital. What will happen instead is that lone pair will stay in an sp3 orbital. So that means we don't count it. And if that's no longer in a p orbital, it's non-aromatic. So the other way you could come to this, which may be a little simpler, is you just look at that and say, well, if it's planar, it's anti-aromatic. It has 7 atoms, it can bend out of the plane, and it'll just be non-aromatic.